this is section 3, and in this section we are going to look at forming differential equation from exponential functions. Forming differential equation, we are coming to concentrate on how to find or form differential equation from an exponential function. If you are given y is equal to exponent a exponent 3x plus b exponent minus 3x. If you are given this equation, now we notice that here we have two terms on the right hand side, and then we have y being the dependent variable, s the independent variable. A and b are constants. Even though the exponent itself is a constant, it doesn't make the whole function here a constant. So it is not a constant per se. So this is an exponential function. Okay, so all that we do here is, since we know that we have two arbitrary constants, we will differentiate. We will name this equation as equation 1 as usual, then differentiate the equation 2 times. Easy calculus. If you are given an exponential function like this to differentiate, all you need to do is you bring the power down, you bring the power to multiply the base, or we apply chain rule approach. So in the chain rule approach I presented previously, we said that this is a function of function where kx is the inner function and then the exponential function is the outer function. The exponent is the outer function, outer function. So the linear function on top is the inner function, and then the exponential function itself takes the outer. So it means the baby is kx and then the mother is the exponent. So exponential function. So what you do is here is that you have to cover the mother and differentiate the baby. So you cover the mother and differentiate the baby. If you differentiate the baby kx with x as a variable, you will get k multiplied by. So then you differentiate the mother exponent. You can assume that this is equal to a or a certain variable. Let's say a, small a. So if we differentiate exponent a, we will get exponent a from our basic calculus. So since we are dealing with a is not the actual function given to us. So this a is representing ks. So it will be exponent kx, not a, because if you differentiate exponent a, we will get exponent a as our answer. So if a is representing ks, then it means that ks will be replacing a. Okay, so that's it. So this is what we are going to do. We are going to apply this to solve this. So if you differentiate this, a y with respect to x, you are going to get dy dx on the left hand side. And if you differentiate this, this is a constant. So if you differentiate this using chain rule, if you differentiate the top, you get 3x. If you differentiate, you get 3. So 3 will multiply a. So, or you can say that if you differentiate the top, you get 3. Fine. Multiplying, now you cover the baby and differentiate the mother. So if you differentiate exponent of a certain variable, you get the same thing. So exponent 3x, and there's a. So we apply this, we can get this plus. Now if you differentiate this side, you get negative 3 again, negative 3 times b exponent negative 3x. And if you simplify, we have 3a exponent 3x minus 3b exponent minus 3x. Here is our equation. We can name this our equation 2. But we said that before to form differential equation from this, because we have two arbitrary constants, we have to differentiate it twice. So we'll differentiate again. We'll differentiate again. So we differentiate again. If you differentiate again, we are going to get the squared y, that's the second derivative, the second differential coefficient as well. So we have, if you differentiate, this is still a constant, a is a constant, so we have nothing to do with this. We have to concentrate on the variable function or the function itself. So we have, if you differentiate the top again, the baby again, you get 3 times, then you have, you use it to multiply 3a, then if you differentiate exponent, a constant exponent, if you replace the 3a, if you differentiate exponent raised to the power a variable, you get the same thing, exponent that variable, and that variable is 3x. But first of all, remember that we differentiate the top before we maintain the exponent. So we differentiate the top and use it to multiply the whole function, the whole term, and then we will place the exponential function again like this. So if you differentiate the top, you get -3, then use it to multiply the whole function again. So you are going to get 9a exponent 3x plus 9b exponent minus 3x. So the squared y be x squared. This also can be written because we have 9a exponent 3x plus 9b exponent 3x. Now we have some terms in common. We have 9 here, 9 here. So we can factorize 9 out and we will get a exponent 3x plus b exponent minus 3x plus b exponent minus 3. Now let's look at this equation 3 and let's look at equation 1. We notice that we have a exponent 3x plus b exponent -3x. So and it's the same as the one in equation 3. So what we do is that we will replace the term in equation, the term in the brackets in equation 3 with y, because the term in brackets in equation 3 is equal to y in equation 1. Okay, so let's proceed. So we are going to put equation 3 or equation 1 into equation 3. In equation 1, we know that we have y is equal to exponent 3x, a exponent 3x plus b exponent minus 3x, sorry. And then also have in equation 3 the square y dx squared is equal to 9 bracket to be a exponent 3x plus b exponent minus 3x. So if you do so, if you put 1 into 3, all that we will get is we will get the square y dx squared is equal to 9y, and this is our differential equation. So we form differential equation. It's simple. Let's look at another one. For example, y is equal to a exponent x plus b. Let's look at this. Here we notice that we have y as a dependent variable, x as the independent variable, b is a constant, and a is also an arbitrary constant as well. But looking at this equation, we can break this exponential function down using indices. Using indices or exponential exponents. So you applying the laws of indices here, we cannot directly say that we have here. We cannot directly say that we have two arbitrary constants. No, we don't have two arbitrary constants. The equation like this has to be reduced or simplified. So we don't have two arbitrary constants here present in the equation. So all that we need to do is to simplify. So applying indices, we see the laws of indices say that if you have a raised to the power x times a again base a raised to the power y, we can write it as, since the bases are the same, we can write the only one single base, and then since the sign between them is multiplication, you add the powers, so x plus y. So it means that if you have something like this, we can write it like this, and you have something like this, we can write it like that, like this, like this, like this, to like this. You can, it's interchangeable, so you can use this to replace this, you can use this to replace that. Okay, so let's come to this. We have this, or we can change it to this. So you can, if you have this can be written as exponent x times exponent b. Now, exponent itself is a constant. Exponent itself is a constant, and b is also a constant. Let's say like 2 is a constant, 3 is also a constant. 2 raised to the power 3 is 8, and now they are all equal to what? A constant, 8. So a constant raised to the power a constant is equal to a constant. A constant divided by a constant gives a constant. A constant minus a constant, or a constant plus a constant, is equal to a constant. So that's what we are going to apply here. So let's look at the equation carefully. So if we have this, then it means that we can let this is a constant, this is a constant, and this is also a constant. So a times exponent, a constant, exponent x. We said that a is a constant, exponent is a constant, b is a constant. So exponent, a constant, is a constant, and a times a constant will also give you a constant. So let's say that k is equal to a exponent b, which is a constant. So we are replacing the constant with another constant, b, k. Okay, so y is equal to k exponent x. So this is the equation that we have to solve. Now here we have how many constants? Only one arbitrary constant. So it means that we don't have two arbitrary constants like we said earlier on. So here, we have to differentiate the equation once to get the first order differential equation. So if we differentiate, we are going to get the y, the x is equal to, and this, if you differentiate k exponent s, we are going to get k exponent x. Because if you differentiate the top, like we did earlier on, 1 times x, if you differentiate 1 times x, you are going to get 1. So it's 1 times, if you differentiate the mother, exponent, a variable, you get the same thing. So you are going to repeat the same function. Okay, so here we have k exponent x as our solution. So this is equation 2. We have to name the first equation 1. Okay, so to do so, now having done this, it means that when you look at exponent x in equation, you can name this one equation 2 and make this one equation 3 instead. So having solved that, having gotten this, if we put k, if you look at k, equation 3 and equation 2, k exponent s is the same as k exponent x in equation 3, so they are equal. So it means that we have to equate them. We have to equate equation 1, 2 and 3. Or we can put equation 2 into equation 3. Either equate or you substitute. So dy dx is equal to y. This is our first order differential equation, which is not, having looked at this, somebody might say that we have two arbitrary constants, but instead of one arbitrary constant, so we have one arbitrary constant instead. Okay, so this is how the solution will be. This is how it will be. Let's look at another one, which is more delicate than this, which is very lengthy but and time consuming. So let's look at this. If you have y is equal to exponent 2x, a exponent 2x plus b exponent minus 3x. If you are given this to form differential equation from, what's the approach? Here we have exponent 2x, exponent minus 3x. It's not the negative 3 here is different from 2, so it will be a bit delicate or difficult to do the formation, but let's go through. Now, to form differential equation from this, we have to first of all identify the arbitrary constant, and we have two arbitrary constants, and we have the variable being one dependent variable and one independent variable. So it will give us an ordinary differential equation. So to proceed, we differentiate equation 1 with respect to x. So if you differentiate, you are going to get dy dx is equal to, if you differentiate this using the fast rule, chain rule, if you differentiate the top, you get 2. If you differentiate down, you get, if you differentiate exponent, the power, you will get the same thing. Having done the first one using chain rule, so you repeat the whole term again. So use the derivative of the top to multiply the down. Okay, so plus you do the same to this one, because if you cover the mother and differentiate the top, you get negative 3. And if you cover the baby and differentiate exponent a constant, exponent x, let's say exponent u, you will get exponent u as an answer. So you will still get b exponent minus 3 as an answer, minus 3x as an answer. Now we have to differentiate the equation twice. So we have dy dx, and here we get, if you differentiate it again, first of all we have so if you differentiate again, you can name this as equation 2. If you differentiate again, we are going to get the squared y dx squared is equal to, if you differentiate this, you are going to get 4, because when you differentiate the top, you get 2 times 2 will be 4. So exponent 2x minus, and differentiate the top, you get negative 3, and negative 3 times negative 3 is positive 9, so it's negative 3, it will be positive 9, b exponent minus 3x. So you have to look at it. you have to apply the same principle like I did. If you still want to do it the basic way, then we have the first derivative, the derivative of this will be 2, and then times. Now you cover the baby and differentiate exponent. Exponent, when you differentiate it, you get the same thing. So it will be 2a exponent 2x minus, then you differentiate the top, you get negative 3. After covering the mother, if you differentiate the top, you get negative 3 times. If you differentiate you cover the baby and differentiate the mother, you get the same thing. Exponent negative 3x, so it will be minus 3. There's 3 there already. B exponent minus 3x. So if you simplify, we are going to get 4a exponent 2x plus 9b exponent minus 3x. So this is the square y, a squared. This is the second derivative. This is the second derivative. Now, we found the second derivative, equation 3. Still, the constants are still in the equation. All that we need to do here is we have to substitute, we have to make either the exponent and then the constant, the subject, and substitute into the other equation, or you can make a or b the subject to substitute into the other equation to get rid of arbitrary constants. So, if you look at this, it's very difficult to, it will be very complex to make only a or b the subject and then use it to do the substitution. Instead, we'll make a exponent 2s the subject, because a exponent 2s and b exponent minus 3s is throughout in all the 3 equations. So it's here in equation 1, it's here in equation 2, and it is here in equation 3. So we can make either a exponent 2x the subject or b exponent minus 3x the subject in any of the 3 equations. So it's simple. So let's proceed as we. Okay then we, from equation 3, we have to make from equation 3 we have to make b exponent minus 3x the subject. From our previous examples, we did similar thing. Like I said, if it's very difficult to make only b or a the subject, so what the best thing is to make b exponent minus 3x the subject, and that will make the equation very simple to form. So we have to eliminate the arbitrary constant, but first of all we have to make sure that we make b exponent minus 3x the subject instead of making only b or a the subject. So to begin, we make b exponent minus 3x the subject. Okay, from equation 3. So from equation 3, if you recall, we have the squared y, the x squared equal to 4a exponent 2x plus 9b exponent minus 3x. So we are making b exponent minus 3x the subject. So from this, we have to send 4a exponent minus exponent 2x to the left. So we have the squared y, the x squared minus 4a exponent 2x equal to 9b exponent minus 3x. Okay then from here we are making b exponent minus 3x the subject, so we have to divide through by 9. If we divide through by 9, we have 1 over 9 the squared y, the x squared minus 4 over 9 a exponent 2x equals to b exponent minus 3x. So we can name this equation 4. Now we can now put equation 4, which is b exponent minus 3x expressed in terms of the second derivative and then the exponential term containing a. So if you put this equation into equation 1 or equation 2, we also have an equation which do not have either b exponent minus 3x, but we can also make a exponent 2x the subject. The main aim is to make b exponent minus 3x the subject in terms of the differential coefficient, not in terms of a exponent 2x. So since there is a exponent 2x here, we have to put the equation into another to find out how best we can do to eliminate the b term or the a term in the equation. So we put equation 4 into equation 2. And equation 2, if you recall equation 2. Okay, so if you recall equation 2, in equation 2 we have dy dx is equal to 2a exponent 2x minus 3b exponent minus 3x. This is equation 2. So we are putting b exponent minus 3x to replace b exponent minus 3x in equation 2. Okay, so we have to replace b exponent minus 3x with the terms on the left hand side of equation 4. So instead of b exponent minus 3x, we are going to substitute minus 1 over 9 d squared y dx squared minus 4 over 9 a exponent 2x. So if we do so, we will get this equation 2. So we have dy dx is equal to 2a exponent 2x minus 3 b exponent minus 3x in equation 4 is equal to this. So if you substitute, we have 1 over 9 d squared y dx squared minus 4 over 9 a exponent 2x. So if we expand, we have 2a exponent 2x minus 3 times 1 will be 3 divided by 9. So it will be 3 over 1 over 3, or 3 over 9 d squared y dx squared. The negative times negative will be positive. 3 times 4 over 9 gives us 12 over 9 a exponent 2x. So in this equation, we have, if we simplify, we have 2a exponent 2x. 3 into 1 is 3 into 3 is 1, and 3 into 9 is 3. 3 into 12 is 4, and then 3 into 9 is 3. So we have minus 1 over 3 d squared y dx squared plus 4 over 3 a exponent 2x. Now we notice that we have d squared y dx squared here. We have dy dx here, and also we have exponent a2 exponent 2x, and we have 4 over 3 a exponent 2x. So we are going to group like terms. If you do so, we have 2a exponent 2x plus 4 over 3 a exponent 2x, or minus 1 over 3 d squared y dx squared equal to dy dx. Now from here, you can straight away add. We have same equal terms, like terms here. So it is 2 plus 4 over 3. Or we can factorize a exponent 2x out of the two terms. So if you do so, we'll get, we have dy dx is equal to 2 bracket between 2 plus 4 over 3, and then a exponent 2x out, or minus 1 over 3 d squared y dx squared. So that's what we have, and we can compute this simply with on the calculator. So we have all this is equal to 10 over 3 a exponent 2x minus 1 over 3 the squared y dx squared. Okay, so we have the y dx is equal to all this. Now we want to make a exponent 2x the subject. So if we make a exponent 2x the subject, just as we did for b exponent minus 3x, instead of making a alone the subject, we have if you make a exponent 2x the subject, we are going to get, first of all, move this one here to have the y dx all plus 1 over 3 the squared y dx squared equals to 10 over 3 a exponent 2x. We want to make a exponent 2x the subject. So what we'll do here is we'll first of all multiply 2 by 3 and then later divide 2 by 10. So if you multiply 2 by 3, you have 3 will multiply this term, the y dx, 3 will multiply the second term, square y dx squared equals to 3 will multiply the last term on the right hand side of the equal sign, 10 over 3 a exponent 2x. This 3 cancels this 3, this cancels that, and we have 3 dy dx plus the squared y dx squared equals to 10 a exponent 2x. So now we'll divide 2 by 10. If we do so, we'll have 3 over 10 dy dx plus, there's 1 here, so 1 over 10 the squared y dx squared equals to a exponent 2x. And we can name this equation 5. Now we have a exponent 2x expressed in terms of differential coefficients, with the exception of we don't have any b exponent minus 3x here or any of the constants appearing in equation 5. So it means that we have successfully made a exponent 2x the subject. Now this is what we had wanted to do with the other equation 4, where we have b exponent minus 3x, which contains a exponent 2x. So what we have to do is we have to put that one, this equation into equation 4. Now we are going to do so because we want to express the constants in terms of derivatives without any of the arbitrary constants appearing on the other side of the equal sign. So the best thing to do is to substitute this into equation 4. Now if you revisit equation 4, we have 1 over 9 the squared y dx squared minus 4 over 9 a exponent 2x all equals to b exponent minus 3x. And here we have expressed b exponent minus 3x in terms of this differential coefficient and then the arbitrary constant a, and that is what we want to avoid. We want to eliminate the arbitrary constants, so we don't want to see any of the arbitrary constants on the left hand side of the equal sign where b exponent minus 3x has been made the subject. So to eliminate this, we have to substitute equation 5 into equation 4. So let's go back to equation 5 and then replace this whole term or this factor in equation 4 with equation 5. Let's do so. We are going to put equation 5 into equation 4. If we recall equation 4, we have 1 over 9 squared y dx squared minus 4 over 9 a exponent 2x equals to b exponent minus 3x. And we said that we are replacing this with the terms in equation 5 on the left hand side of equation 5. So if you do so, we have 1 over 9 the squared y the x squared minus 4 over 9 a exponent 2x is now 3 over 10 the y dx plus 1 over 10 the squared y the x squared, and all equals to b exponent minus 3x. So this is what we have. So now we can simply express b in terms of the differential coefficients. So we have 1 over 9 the squared y the x squared minus, if you multiply this to that, we have negative times positive is negative, 9 times 4 times 3 is 12, 12 over 9 times 10 is 90 dy dx. Similarly, negative times positive is negative, 4 times 1 is 4, 9 times 10 is 90, and we have the squared y dx squared, all equals to b exponent minus 3x. Now we have similar terms in this equation. So what we need to do is we have to make sure that we have only one similar differential coefficient appearing in the equation. So all we need to do here is to bring or merge the first term and then the third term together. So we have the squared y dx squared here, we have the squared y dx squared here. So we have to group like terms and then simplify. So we have, if you do so, we have 1 over 9 the squared y dx squared minus 4 over 90 the squared y dx squared minus 12 over 90 dy dx, all equals to b exponent minus 3x. This is what we have, and from here we can factorize the square y dx square out and then further simplify these two numbers. So, or you can use the calculator to just subtract. Okay, so if we simplify the last line, on the last line we have 1 over 9 minus 4 over 90 the squared y the x squared. If you choose to factorize, minus 12 over 90 dy dx equals to b exponent minus 3x. Okay, so with the calculator you can simplify this easily. So we have 1 over 9 minus 4 over 90 gives us 1 over 50 the squared y dx squared. Okay, minus 12, and 12 over 90 can be simplified. So 12 divided by 90 will be 2 over 15 dy dx equal to b exponent minus 3x. So this is what we have for b exponent minus 3x, and this is equation 6. Now we've been able to make b exponent minus 3x the subject, and then the other terms on the left hand side of the equal sign does not contain any of the arbitrary constants. So, and similarly, in equation 5 we had 3 over 10 dy dx plus 1 over 10 the squared y dx squared equal to a exponent 2x. In this equation also, we have expressed a exponent 2x the subject in terms of the arbitrary, in terms of the differential coefficient in the absence of the arbitrary constants. So now we are safe to go. So now we are going to substitute equation 5 and equation 6 into equation 1. Because we have not altered equation 1, we have not touched equation 1, we have not used it for any other purpose. So we are going to substitute equation 5 and 6 into equation 1. So why are we doing so? One may ask. Now in this equation we have the arbitrary constants here in equation 6. In equation 5 as well, we have also arbitrary constants a exponent a exponent 2x, okay, expressed in terms of the differential coefficient. So still we have the arbitrary constants here, and our main aim is to eliminate the arbitrary constants. So what you do is you have to substitute or put equation 5 and 6 into equation 1. If we recall equation 1, we have y is equal to a exponent 2x plus b exponent minus 3x. This is equation 1. And in this equation, we have a exponent 2x containing the arbitrary constants, b exponent minus 3x also contains the arbitrary constants, b and a respectively. Now, so our main aim is to eliminate the arbitrary constants. So once we got into this level, and we have an expression that can be replaced, or that we can use to replace the arbitrary constant, or the terms containing the arbitrary constants in equation 1, then it means that we have to substitute equation 5 and 6 into equation 1 to take that effect, or to effect that change. Okay, so if you do so, we have y is equal to a exponent 2x in equation 5 was 3 over 10 dy dx plus b squared y dx squared equals to a exponent 1 over 10 a exponent 2x. This was equation 5. And now in equation 6 we have this. So we are going to replace this with this. And we'll have 3 over 10 dy dx plus 1 over 10 d squared y dx squared. That's this. Plus equation 6. In equation 6 we have b exponent minus 3x is equal to 1 over 15 d squared y dx squared minus 2 over 15 dy dx. So 1 over 15 d squared y dx squared minus 2 over 15 dy dx. So in this we have eliminated the arbitrary constants. So this is the new equation we have, but we have to simplify. We have this first differential coefficient here. We have also the first differential coefficient here. We have the second derivative or the second differential coefficient here also. We have the second differential coefficient. So we have to group items and simplify. So finally, we have y is equal to 3 over 10 dy dx minus 2 over 15 dy dx. So the first derivative and then the first derivative together plus, now we are going to group the second derivatives. We have 1 over 10 d squared y dx squared plus 1 over 15 d squared y dx squared. So if we simplify this in a similar manner, it is 3 over 10 minus 2 over 15. So, or we can try to factorize. So it to be 3 over 10, we are factorizing dy dx out. So we have 3 over 10 minus 2 over 15 dy dx. And in our previous section, I talked about, or I explained why we normally put the dy dx behind the brackets. We said that if you have dy dx, if you have something like this, the differential operator, and then a function, okay, after which, then it means that we are coming to perform differentiation. But if you are done with differentiation, we put the differential coefficient behind. So if you are done with the differentiation like this, we put the differential coefficient or the differential operator behind, which means we have finished performing the differentiation. So we don't put it in front to look like we are coming to perform differentiation. We are done with differentiation, so we put it behind. Okay, let's proceed. So plus, now we are going to factorize the second derivatives outside. So we have 1 over 10 plus 1 over 15, then the squared y dx squared. If you compute this on the calculator, we have 3 on 10 minus 2 on 15 will give us 1 on 6 dy dx. Now if you compute this also, we have 1 on 10 plus 1 on 15. We have 1 on 6 the squared y dx squared. So we have y is equal to this, and that gives us our differential equation. So we have formed differential equation from the original equation given by a exponent 2x plus b exponent minus 2x successfully. And in this equation, we don't have any of the arbitrary constants represented. So finally, this is our second order differential equation, having the second derivative here as the highest derivative throughout the equation. So